So we've now hit a inflection point in our study of mechanics. With having explored Newton's laws of motion, as long as we have a good model of the underlying force laws, in principle we can describe the motion, the classical motion of anything. The practice, though, can be a little rougher. This is because most macroscopic objects are made up of very, very large numbers of atoms. And so although in principle you can go and apply Newton's laws of motion to each and every atom, in practice that's just computationally intractable. There's no way it can be done. And so where we're heading going forward is taking a look at tools that will allow us to have to avoid that at least somewhat, and make things more computationally feasible. But we're not particularly introducing anything new, just new ways of doing what we've already been doing. So to this end, we're going to first start taking a look at studying the rotation of objects. And I've mentioned before that there is a spiffy little demonstration that for a rigid object, you can completely describe its motion as the translation of its center of mass combined with its rotation about its center of mass. This takes you from having to look at on the order of 10 to the 23rd variables, keeping track of each and every atom, down to at worst 6 and usually more like 3. So that's a great simplification. But in order to do that, we have to first come up with ways of describing how things rotate. And to that end, we'll start by thinking about angular position. So as a quick refresher from trigonometry, we will go ahead and remind ourselves how an angle gets defined. So in trig class, usually the way we defined our angles was we said if we want this angle here, theta, we can define the angle theta to be the ratio of the arc length that we took off of the reference line, which is usually the plus x-axis, and that arc length is usually denoted s. And we divide it by the radius. And this will give us the angle in radians. Now, an important practical note here about radians. Radians are not, strictly speaking, a physical unit. They are a symbol. And what do I mean by that? Well, if we take a look at the definition here, arc length is going to have units of meters. Radius is going to have units of meters. So officially, the meters just cancel out and the angle is just plain a number. That can get really confusing, though. So usually people write RAD for radian, literally to remind themselves that they're working with an angular quantity. Now, since radian doesn't actually have a physical dimension, when you're balancing your units, you're checking your units, you're going to have to treat the radian symbol like it's the number 1. So you're going to find that radian symbols will appear and disappear, and it's okay because it's just a thing that's reminding us that we're working with an angle, and it isn't actually a unit. Okay, so one thing that physicists need to do, though, is we have to keep track of the history of the motion of something. So our angles have a Chern counter. So for instance here, if this is my reference line here, this angle right here would be pi, would be pi radians. And this angle here would be 3 pi radians. So we're keeping count of the fact that the object went through 1.5 turns as opposed to half a turn. Now, as far as trig functions are concerned, you'll get the same answer either way. You take the sine of pi or you take the sine of 3 pi, you get the same answer. But as far as trying to describe how fast something is spinning, for instance, it's going to really matter whether it turned through pi in a certain amount of time or 3 pi. So we have to keep track of the turn counter. Also, there is a convention for signage. Again, you are free to specify otherwise, but if you do otherwise, you do have to specify it. The convention is that angles that are going off counterclockwise from the reference line are positive and clockwise is negative, which may seem a little counterintuitive, but that's just how we roll. There are 2 historic reasons for this. One of them is if you point your right thumb towards you and you look at how the fingers of your right hand curl, they curl counterclockwise. And the other is if you look at the Earth from outer space above its north pole, you'll see that the Earth rotates counterclockwise. So for those 2 historic reasons, physicists found it more convenient to define positive angles to be counterclockwise and negative angles to be clockwise. And the math community came to similar agreements. But if it is more convenient for you to do it the other way, that's fine. You just need to say that out loud. Okay. So I've already alluded to angular velocity. So this is talking about how fast something is rotating. And it's defined in analogy to translational velocity, but it is not the same thing. This is talking about how fast something is spinning, not how fast it's moving. So the definition of angular velocity, and this funny thing, loopy thing right here, let me try to draw a really good one, at least the first time, is a lowercase Greek omega. You draw it like that with a little loop-de-loop in the middle. It is not a W. And since W's do show up as the symbol for work, it's important to be able to tell the 2 apart. Anyway, this is defined as the limit, as our time intervals go ever shorter, of the rate of the angular displacement, the change in the angle, over the change in time. So our typical units for this will be radians per second. And again, keep in mind, radian is just a placeholder that reminds you that you are working with an angular quantity. It doesn't actually, so when you're checking your units, like I say, you'll just imagine it's the same difference as inserting the number 1. But it is important here to write that radian. Another quantity that we'll run into called the frequency is the number of oscillations per second that something will do. And oscillations don't have a dimension either. This can get so confusing that the physics community has pretty much decided never to write 1 over seconds or seconds to the -1 for either quantity. We write radians per second when it's an angular quantity, and we write hertz, capital H, small z, if it's non-angular quantity. And that's just to double dog sure that we keep the two straight. So if we are rotating counterclockwise, the angular velocity will be positive, and if we are rotating clockwise, it will be negative. And we can certainly start to do things like draw a graph. We can take a look at what it would mean for something to be rotating uniformly, for instance. So here we can go ahead and make a graph of angle versus time. And if we're rotating uniformly, that will be a straight line. And the corresponding angular velocity versus time graph would be a horizontal line. And again, here, you're free to slide this up and down as much as you like. As long as it's a straight line, that's fine. With a positive slope, this will mean a positive value for our angular velocity, which will mean we're rotating counterclockwise. If we were to have a negative slope here, whether it's above or below the axis, doesn't matter. The angular velocity would be negative, and it would mean that we were rotating clockwise. And we would be doing this at a constant angular speed. So here's where we can start to tie things together. And so as a working example here, I'm going to imagine that we have a ball at the end of a string. So let's say I've got a ball at the end of a string and I'm whipping it around in a circle. The string has radius r. That's supposed to be a circle. Sorry about that. We've already seen that the direction of the velocity has to be tangent to the trajectory. So here I'm saying we're going counterclockwise, but we could just easily be going clockwise. It doesn't really matter. So we can figure out how fast this is by looking at two subsequent periods of time in the orbit. In this small amount of time, delta t, the stopper would have traveled an arc length delta s. And also, the stopper and string would have gone through a matching small angle, delta theta. So we can say that the speed is the limit as delta t approaches 0 of the change in arc length with respect to time. Now, if we go back to what we had before, here we said that angle is arc length over radius. So I can times both sides by the radius and get that the change in arc length would be equal to the radius times the change in angle. Now, since the radius is a constant here, it doesn't matter whether we take the limit of the radius times the change in angle, or if we take the limit of just the change in angle with respect to time and then later times it by the radius. So I'll just go ahead and do that. So my speed would be equal to the radius times the limit as delta t approaches 0 of the change in angle with respect to time, but we look at that and say, hey, wait a minute, that literally is the definition of angular velocity. So we end up saying that the speed is equal to r omega. And some books will put a little sub t here for tangential at this point. And this gets called the tangential velocity, which it really should be called the tangential speed. But for whatever reason, people call it the tangential velocity, even though it's just the magnitude, so it should be the speed. But there you go. People are weird that way. Now let's go and check units here, just to make sure that we do indeed get a speed out of this. So our first question here is, okay, a speed has to have units of meters per second, right? So let's see, does it match what we've got here? This is meters. Then this is radians per second. Oops, RAD per second. And you might look at that and say, crap, that doesn't match up. But remember, the radian is not a unit. It's just a placeholder that reminds you that you're dealing with an angle. And whenever you see a radian, just substitute it with the number 1. And then you see, oh yeah, sure enough, if I take meters times 1, that's just meters. So meters per second equals meters per second. Yep, the units check. So just to maybe make this a little more concrete, let's imagine like a 19th century factory. In those 19th century factories, if you've ever gone on a tour of the ones that have been rebuilt, you'll know that usually there was one big steam engine in the middle of the factory somewhere that had a huge pulley on it. And then there'd be a big honking fan belt that was attached to that pulley. And the fan belt would run basically through the entire factory and churn some smaller pulleys in order to run whatever machinery you had at the workstation. So let's say the one on the steam engine here, we'll say this is pulley A, has a radius of 1 meter. And we'll say that the smaller one here, we'll say it's pulley B, has a radius of 0.5 meter. And we'll say that these are tied together by a fan belt. So let's say that this is rotating counterclockwise at 10 radians per second. What I'd like to know is what is the rate at which the other pulley will rotate. From our intuition, we already know the direction. We know it's going to be counterclockwise because of how the fan belts were attached. And when you look at this, you realize that the trick to this is that if I look at a small chunk of fan belt here, this small chunk of fan belt has to be moving at the tangential velocity of this pulley. But so is every other chunk of the fan belt, or else it would be stretching. So that means, for instance, this chunk of fan belt right here where it's attached to the pulley also has to be moving at that same tangential velocity. So we can demand that the tangential velocity of a point at the end of pulley B be equal to the tangential velocity at the end of a point on pulley A. Okay, so we can put in, this will be the radius of pulley B times the angular velocity of point B. And remember, physicists say angular velocity, even though we should really say angular speed. RA omega A. All right, divide through by RB. So we have 1 meter over 0.5 meter times 10 rad per second. Meters cancel, and we are left with 20 rad per second. And that should match our intuition here. You know, we know from things like, say, turning a bike crank or something like that, that you don't have to turn the pedals around as many times as the wheel goes around, because the cogs in the back of the bike are smaller than the chain rings where the pedals are. Alrighty. So in the next video, we will start to take a look at centripetal acceleration and see where, and also talk a bit about angular, talk a bit about fictitious forces for just a bit. Catch you in a bit.